Hello, everyone. Um, First of all, let me thank you to all the attendants that are interested in this webinar. This is the first webinar of a series entitled Enterprise Application Performance. And today, I'll be talking about application performance when using server push technologies. First, let me introduce myself. My name is Tito, and I'm a solution architect from OutSystems experts team. I frequently do architecture and performance analysis of client systems, and have found many client applications suffering greatly because they don't apply existing server push technologies. This kind of technology has been in the market for quite a while and has reached a state where it is well supported by mainstream browsers and community frameworks. Now, let's dig into this thing. Some of you might have seen applications affected by performance issues where users complain about load times or poor user experience due to the lack of real-time data feedback. This is very common in applications that continuously pull the server or database for fresh data. And many times the root cause of that such poor performance is related with the high number of database accesses or queries, or even with poor client-side programming or abuse of polling mechanisms done in JavaScript client-side code. Very often, the database or the network is pointed out as the cause for the poor performance. But when there is a client-side polling involved, usually the culprit is the number of times an operation is being invoked on the server side, which in turn can execute a high number of database operations. First of all, to give you some context about the problems that push technologies intend to solve, let's imagine a scenario where we have a web application that needs to refresh its data every second. In this scenario, using normal HTTP requests, the client browser has some JavaScript code that invokes a server-side operation continuously inside the loop. That server-side process usually executes a query against the database to verify if there's new data. All right. This technique of continuously querying the server is called pooling or load pooling. As a consequence, if the server-side operation or query is heavy, it can lead to performance issues. Usually, the long polling request sends some state, probably the type of data it wants to verify, and the user session ID to identify its user. A single request like this often requires one or more database queries, one to load the user session and a few more to check for new data or execute business operations. If the user session is loaded from the database and changed, there's still another query that is executed to save the session back to the database. So these polling operations are executed continuously on a very short interval. And due to that, there will be a performance penalty that increases as the number of concurrent users start to grow. Yes, there's a solution for this kind of problems, which is making the server as the initiator of sending data to the client without having previous requests like the previous scenario. This technique is called push because the data is pushed from the server without the client making a request for it. To support this kind of technique, a permanent socket from the browser to the server is kept open to allow the server to push data to the client until the socket connection is closed by application code or when the browser closes. Since the server is the one that knows when there is new data to send to the clients, there is no need for continuous requests from the client side. Another difference is the type of connection and protocol that is used. In this case, the client uses a normal HTTP connection to upgrade its connection to the WebSocket protocol. This sort of protocol is minimal overhead, and the main web browsers support hundreds, if not thousands, of connections like this. So using a push technology like WebSockets, the browsers can open a WebSocket connection to the server that is identified by an IP address, port, and recipient ID, which is like a topic or a channel name, and that can be used by the server to identify a very specific client and send data to him. So the WebSockets protocol had a rough start, and many think that the technology is quite recent. But the first draft was done back in 2009, and at the time it was named ICSI, which stems from the author Ian Higson. WebSockets protocol only got a standard classification in 2011. So this is one of the biggest reasons why it was hard to have mainstream adoption by the browsers back at the time, as we are going to see on the next slide. For the most curious ones, HTTP 2.0 only got published in 2015 and is also going to play a major role in improving the performance of web applications going forward into the future. As we can see from the history, the protocol standard classification was obtained only in 2011, and this is why major support for it was only seen in browsers after that date. For instance, Internet Explorer 7, 8, and 9 do not support the WebSockets protocol because Microsoft released these browsers a few years sooner than 2011. Firefox only got official WebSockets support with version 11, which was launched in 2012, and Chrome in the end of 2012 with version 16. You can see them here because they have launched many versions, but the green boxes mean that the WebSocket protocol is supported, and the yellow greenish ones mean that it's partial supported, and the red ones that is not supported in any way. What we need to remember is that WebSockets is a protocol and essentially allows two-way communication between the client and the server over a TCP/IP socket. The main goal of the WebSockets is to solve the problem of opening too many HTTP connections like normally done when implementing long polling techniques. HTTP 2.0 is also going to minimize this kind of situation, since it uses multiplexing techniques to send data through the same socket. There is a big difference between HTTP and WebSocket requests. In HTTP, the client issues a request and then it waits for a response from the server. If there are no more requests in the pipeline, the browser or the server will close the socket. If after a few seconds a new request is done, a new HTTP connection and respective TCP/IP socket will be opened again. Due to this fact, TCP sockets are opened and closed continuously, and that process is associated with a performance penalty of a few milliseconds depending on network conditions. On top of this, most of the mainstream browsers only support a small number of concurrent TCP sockets to the same domain, between 6 and 12. So the normal HTTP request should not be used to implement concurrent pooling operations, since it uses the same browser HTTP connections that are used to fetch images or HTML code. With WebSockets, however, a permanent connection is obtained after an initial handshake, and information is exchanged without the need of opening further TCP/IP sockets. The WebSocket connection can be closed by application code, JavaScript, or when a browser is closed. So there is also an internal ping control frame that can be used to keep the TCP/IP socket alive during communication. All these control frames are defined as part of the WebSockets protocol. All right. So all these ping messages that we have here, they are used to maintain an open WebSocket connection from the browser side. WebSockets allows to minimize these latencies in the response. When the browser client is doing too many requests to the server, which is usual when implementing load pooling techniques or concurrent requests, there is no additional TCP/IP handshaking with WebSockets. So this benefit gets even more visible as we start to escalate the number of requests or messages as seen by these numbers. So there's a big difference if we go from 10 messages to 100 messages. For instance, it takes 112 milliseconds using normal HTTP requests or REST requests, and it only takes 20 milliseconds using WebSocket packets. So this is like a 5 or 6 times increase in performance. For 100 messages that were exchanged between the client and the server, the message payload is very important in ensuring that we get a performance benefit from using WebSocket, as we're going to see in the next slide. In this case here, in this situation, the benchmark was done using a constant payload of 1 kilobyte and an increasing number of messages. This chart, however, shows the biggest benefit of WebSockets are when the message payload is small for a significant amount of requests. This is true because HTTP 1.1 has built-in optimizations to send large amounts of data, since the same socket is reused in these conditions. So in this situation here, we start to see a smaller difference as soon as we start to increase the payload in bytes. So the benefit of using WebSockets start to decrease as we increase the payload size. So one needs to be careful when choosing the technology. To get deeper into the inner workings of how to initiate a WebSocket connection from an HTTP request, this is what needs to be done. You don't need to worry about this. This is simply a deep dive of what's happening over the wire. Basically, the request is a special HTTP upgrade which has the headers update WebSocket and connection upgrade, as well as an initial handshake key that is used in the response to verify that a successful connection is made. The connection upgrade header has implications when using proxies that will be explained later on. The other special header, WebSocket protocol, allows the negotiation of subprotocols, and it is out of the scope for this webinar. So, when can we use WebSockets? There are a couple of recommended uses. In essence, to mitigate functional or to implement functional requirements on scenarios where web applications need to present server data that is constantly changing, like, for instance, real-time data updates or stock price tickers, notifications to users, or even results from background processing tasks. One should, however, consider that WebSockets should not be used to send HTML or large amounts of data, as mentioned before, but instead small bits of information. WebSockets can also be used to address architecture restrictions, like the infamous 6 connection per host limit imposed by some browsers, especially when implementing load pooling techniques. Using standard JavaScript, HTTP requests to implement concurrent pooling requests can lead to starvation of the available browser HTTP connections to the same domain. Another reason to adopt WebSockets might be the communication with local services to access native resources. For instance, a Windows service that implements a driver for a biometric authorization device or a card reader could expose a simple WebSocket to send information back to the local browser page. So how can we integrate WebSockets with OutSystems? This depends whether it's an integration with a WebSocket Cloud service or an in-premises installation of a WebSocket server farm. For a cloud-based WebSocket service, usually the provider exposes a public server-side API besides the JavaScript client-side framework. This server-side API can be called from .NET or Java applications, and it allows OutSystems applications to push data to the browser indirectly. These kind of cloud services usually provide some sort of authorization that is token-based or some sort of an API key, and should also support secure transport channels using TLS or SSL, which, by the way, is called secure WebSockets. Another important recommendation is to pick the service that has a lower latency for the most of the target users, and also for the OutSystems infrastructure. So you need to be wise, and you need to measure if you go forward with a third-party cloud service that provides you WebSockets technology. You need to measure and take into account the latencies to pick the best solution and provider for your case. This example depicts a possible integration with a well-known WebSocket Cloud service like Pusher.com. In this example, a background process, which can be a timer or can be triggered by a BPT event or an entity CRUD operation, is running inside the OutSystems front-end application. And it's going to publish data to a client or a group of clients using the server-side Pusher.com API. This can be done. This sort of functionality opens an entire spectrum of integration possibilities. In this case, the blue arrows represent normal HTTP requests and responses that are distributed by the load balancer to the front ends, to the OutSystems front ends. The OutSystems web applications that are interested in receiving notifications through WebSockets only have a simple Pusher.com JavaScript that is subscribed to those events, as we can see in these boxes here. The entire WebSocket infrastructure is provided by Pusher.com, and it's extremely easy to integrate with, as I will show briefly. The authorization with the Pusher.com service is done through an API key that is used from the JavaScript code and also from the server-side API. In this situation, an organization is hosting the OutSystems infrastructure and doesn't need to care about how the infrastructure is supported. It is simply provided as a service by with a predetermined SLA by Pusher.com. In this situation here, the red arrows mean that it's normal HTTP requests. It can be screen requests or AJAX requests to the front-end servers. These clients here can also call operations in the front-end servers that can send information back to other client browsers using the same cloud service. So what this means is that it's possible to have communication between different client browsers using this sort of service. A chat application is a good example of this. For WebSocket Cloud services, there are many providers in the market, and the list is growing every day. Pusher.com is quite easy to use as well as PubNub. They both have a big client base and success stories, so please have a look at them. Fanout.io is also getting some momentum and is worth having a look. Both providers have free accounts that you can use to test your integration, and the cost of the service is quite acceptable for an organization that without even taking into account the effort and cost of maintaining a self-hosted WebSocket farm. Please look at them before considering implementing your own WebSocket server infrastructure. For self-hosted WebSocket servers, the infrastructure that supports the WebSockets should be dedicated. I mean, not installed in the OutSystems front-end servers. Simply put, the resources required by WebSocket servers are quite different from the ones that OutSystems front-ends require. The WebSocket server can scale differently depending on the number of connections that are made to them. On top of that, it's wise to isolate this type of service from the front-end resources used to present the screens to the users, because they have special network requirements and can be installed in different or many different operating systems. One of the most important aspects of integrating with WebSockets is to provide a REST service on the WebSocket server that is used by the OutSystems applications. This is used to push notifications to the browser clients. And finally, don't forget that some sort of token-based authorization should always be implemented in the WebSockets, especially if they are exposed to the public. This is made in order to avoid denial of service attacks or other kind of security flaws. As you can see, this configuration is completely different here. In this example, a self-hosted Signal R server cluster is used to implement high availability in the WebSocket farm. Signal R is a framework that supports the WebSockets protocol and can be installed inside IIS or in a standalone .NET web server. In this configuration, it is still recommended to keep the WebSocket servers outside of the OutSystems infrastructure. The existing load balancer can still be used to distribute the WebSocket requests to the specific Signal R server by using either sticky sessions, or if that's not possible, then it's a backplane server must be used, like the one we have here that is using SQL Server. This kind of server allows any Signal R instance to handle the client connection. Signal R supports many types of backplane servers like SQL Server, Redis, or Azure Service Bus. As you see, it's not simple to implement a high availability WebSocket cluster, and that is why it should be kept on a dedicated infrastructure. Opting for the cloud WebSocket service does pay off most of the time, since development teams don't have to worry about such infrastructure details. There are many providers and frameworks to implement self-hosted WebSocket farms. One of the most well-known implementations is the Socket.io plugin for Node.js. Signal R is also adopted by the .NET community as a preferred WebSocket server. Its deployment requires Windows Server 2012 R2, because otherwise the browser clients will do a fallback to different mechanisms that don't use WebSockets. There is also an IIS node, which is a working Node.js implementation that sits inside a dedicated application pool in IIS. SuperSocket is also a well-known library for building custom WebSocket servers in C#. It can be used easily inside a custom Windows service, for instance. There are many other solutions in the market. This one here, the WebSocket daemon, is only for Linux, and it's available in many distributions. So, some considerations that are worth having when using WebSockets. WebSockets have compatibility issues with HTTP proxies. I mean, when the client browsers use a proxy server, there can be issues with the connections. This is due to the way the HTTP upgrade works, and this HTTP upgrade header is also used for to initiate an HTTPS connection. So some proxies might drop the initial WebSocket handshake because of that. In terms of security, always promote TLS SSL for the OutSystems applications. With this approach, most of the WebSocket frameworks will use secure WebSockets by default. It's important to mention, however, that WebSocket servers can also be the target of denial of service attacks. So the same DOS prevention mechanisms should be in place for exposed self-hosted WebSocket servers. The authorization and authentication should be taken care of by the WebSocket framework that you are using, since this is not something that the WebSocket protocol defines. If you are not using a well-known framework or cloud service provider, then you have to implement some sort of token-based authorization or an API key to control user access. If you're implementing a self-hosted WebSocket farm, you will have to take into account the cross-site support. For example, Signal R by default checks the origin header to verify if the script origin is the same. Special care has to be given to configure Signal R to allow cross-site connections. This means that, for instance, in that example of the OutSystems application that is using a self-hosted WebSocket server, if the WebSocket server URL does not have the same domain, most probably the Signal R server is going to block the connection, and the OutSystems application cannot create a connection from the browser client-side code. This is one of the most important. You should always check if you're effectively using WebSockets instead of a fallback mechanism, sorry. Most frameworks will fall back silently to long polling techniques if the browser does not support the WebSocket protocol or if there's a misconfiguration in the server. You should always use the browser developer tools to check if the WebSocket protocol is effectively used, like in this picture here. In this case, we're using Google Chrome developer tools, and there's a tab in there to check if the existing WebSocket connections are being made or not. So for instance, if you have a client browser that does not support or a misconfiguration on the server, you will not see any resources being used on this tab. Another thing worth taking into account is that some browsers might have specific tweaks or different WebSocket implementations. So always use a well-known WebSocket framework or provided JavaScript code instead of writing your own implementation, even if you think that you're really smart. I'm saying this because of most of the well-known frameworks, they implement fallback mechanisms that support other technologies besides WebSockets. This will make sure that all of the mainstream browsers, even older versions, support your application. So this is always a good idea. That's it. Now let's see some WebSockets in action. I will now show you how we can easily integrate a WebSocket Cloud service like the one from pusher.com. All right? So let me check the application here. I've made an application that is related with something very important nowadays. And basically, what this application is, it's for the European Union membership of Great Britain. So we have two charts in here that are getting information from the server side. Now, imagine a scenario where people are being asked what their opinion are or how they're going to vote. And this is being done in real time. This is what we're trying to simulate in here. So we have an application that is completely different and that writes on the database the votes that people are doing. So whenever I click in this button here, vote, I'm going to generate votes and record them into the database. The point here of showing you WebSockets is that whenever I change or I click here in vote, you'll see an update of the interface automatically. And you don't have any sort of pull mechanism doing long pulling, as we will see. So let's do a refresh now to see if everything is working. Let's hope so. Great, fantastic. Now I'm going to issue and simulate. This actually generates random votes between 0 and 200 for these three specific options, which is remain, leave, and undecided. Unfortunately, I didn't give a preference to any of these, so it will be completely random. So, as you see, I've clicked in the vote button, and we automatically see that the interface got updated in here. So we generated a couple of votes. Let's do it a couple more times, and as you can see, this is being done very fast with very low latency. I will even increase this to a bigger value so you can see it better. Yeah? So imagine that this kind of application could be, for instance, a stock ticker. You would see the application refreshing all the values without doing any server-side requests. I'm going to open the developer tools here. Let me see if I can show them. It's a bit slow at the moment. Unfortunately, Google is refusing to open the developer tools. Let's see if I can show it in another way. Or let's try close the browser and open the browser again. Unfortunately, I cannot open developer tools. I don't know why. Let me try with Internet Explorer. All right. This one works. That's great. I'm more used to the Chrome developer tools than the one from Microsoft. So let's see if I can show you that we're having here a WebSocket connection. All right. So we should see here somewhere. All right. So we're getting these events from the server side. And basically every time that I click in vote, we get a new total count with all the different values for the charts. So the charts are being updated by a specific script. Now, let's close the Internet Explorer tools. In the meantime, let's see if I can understand why developer tools is not working. Let's see here, tools, or in the new one. Let me see if I can open it in here. It refuses to open. Maybe it's because of the monitor. Let me see. No. Unfortunately, I cannot show you that picture that I was referring to of the developer tools of Chrome, of Google Chrome, where it shows that we are using effectively the WebSocket protocol. But anyway, despite of that small issue, I'm going to show you a bit of the code. So this is the application that we did for this demo. It's a very simple application. We only have the home page in here, and it has two charts. And then we integrated with pusher.com using a script that is provided by pusher.com, and the script is in here. As you can see, this is just the lines that we need to put on the JavaScript side. This is a local JavaScript function that is responsible for updating the charts and the table of and the summary table with the statistics of the survey. So all this stuff here is provided by Pusher framework. And what is important here to mention is that we have an application key that is generated dynamically on the pusher.com back office, and we have to use that application key when we initialize the Pusher script. So if we don't do that, Pusher will refuse the WebSockets connection, all right? Also, we have to define a channel, which is something that identifies the source of the information that listeners can bind to. And from that, you can bind to specific events. And we have a specific event that was created just for the survey data. So this is just the couple of lines that we have to support the WebSockets inside a JavaScript or a web application, right? Now, the rest of the script that we have here is very simple. This is what is done to update the charts. There's nothing here specific to WebSockets. This is just JavaScript to update the DOM and the charts, nothing more. Another thing that we have here is that the pusher.com script we need to add to the home page a script that has all the entire JavaScript that consists of the initialization code of the pusher.com library. If I'm not mistaken, it's not this one. It should be here somewhere. Let me see. Interface. Probably it's in the preparation. Here it is. So this is what we need to add, and this is a minified version actually of the pusher.com library. And with this, you add it on the preparation, and then you can invoke that simple script that I was showing to you that is in here. So that JavaScript URL downloads the script, and then you can invoke these lines here to bind to WebSocket notifications, all right? There's another interesting thing I would like to show you, which is whenever you use a cloud provider, you have many sorts of tools. In this situation here, what we have, let me refresh the page. This is the actual back office of the pusher.com cloud service. And from this, you can see everything that is happening. This is the actual request we made a few minutes ago. So if we start doing more requests, we will see an increase on these charts. So you can create your app, and you can configure your app to use WebSockets that are provided by pusher.com. And you have many things that you can configure. You can configure a specific application key. You have debug console. You can do many sorts of tests with it. And you even have examples of it. And it's very easy to use. Another thing that is important to mention is that this kind of charts allows you to keep an eye on the open connections. And this is very important because with that, you know if it's time to escalate your WebSocket farm. I believe I've shown everything that that is important for you to do an implementation. Pusher.com is just an exercise. There are many others out there. Please have a look at them. I find this one very easy to use.